All right, section 2.7, absolute value functions and their graphs. So the simplest example of an absolute value function is given by the equation f of x equals the absolute value of x. So this is the parent function for the absolute value. The parent function, or the graph of an absolute value function, is V-shaped and symmetric about a vertical line called the axis of symmetry. So in this case, that graph is going to have a single maximum point or a single minimum point called its vertex. And you learned about the absolute value graph in Algebra 1, so hopefully you remember some things. And we're going to apply that and then expand upon your understanding of absolute value. So this is a good example of the absolute value graph. It's your V-shaped graph. This is your parent function. So if you put in a -3 into the absolute value, the output in this case is 3. So you would plot the point -3, 3, and so on down the list, applying your absolute value. This question wants us to graph the absolute value function. It says, what is the graph of y equals the absolute value of x minus 4? How is this different from the parent function, or in this case, y equals the absolute value of x, or in this case, f of x equals the absolute value of x? So let's just graph this and we'll see how it compares. One way that you can think about this, we can make an xy table to get our values. So if we put in an x, we put y, we got -3, -2, -1, 0, 1, 2, and 3. So if we're plugging in these values, we should be able to finish our table of values here. And so for this particular function here, this is our table of values. And so we can go ahead and graph this. We're going to go ahead and graph this on our coordinate plane here. And this is our graph. And then they ask, how is this different from the graph of f of x equals the absolute value of x? Well, if we think about this, this is our parent function for the absolute value. So that graph looks like this. So I'm going to go ahead and graph it in black here. And what we should recognize is the way this looks different. Oops, didn't mean to do that. The way this looks different is that your graph of y equals the absolute value of x minus 4 is translated down 4 units. Here this says, what is the graph of y equals the absolute value of x plus 2? So here we can go ahead and create a table of values if we want. If it helps you graph, you can do it that way. I recommend using -3, -2, -1, 0, 1, 2, and 3. And when you plug in those x values, you get your outputs as 5, 4, 3, 2, 3, 4, 5. And so we can graph this one as well. So we'll graph it in red. So there's one branch, and there's the other. So this is our absolute value graph. And then if we remember from the previous slide, or just in general, our parent function for the absolute value looks like this. I'm not going to color this one in. I'm just going to draw the dots. So it looks like that. And so hopefully at this point we're starting to recognize how this part of the graph is affecting our absolute value functions. So in this case, y equals the absolute value of x plus 2 is translated up 2 units. So here's a good reference piece for how all of the various translations and stretches and compressions and reflections take place with the absolute value. This is a lot like what we saw in section 2.6, except now we're applying it directly to absolute value as opposed to just general functions. So your vertical translation is when you're either adding or subtracting a constant on the outside. When the constant becomes inside the absolute value with the x value, now you're seeing a horizontal translation, both left and right. And then vertical stretch or shrink in this case would be when you have a stretch will be when you have an a value multiplying by the absolute value that is greater than 1. A compression or shrink is when you're multiplying by a value less than 1 but greater than 0. And then a reflection, you'll see here, very similar to what we saw before. When it's over the x-axis, you're seeing that the negative is affecting the things on the outside of the absolute value. When it's over the y-axis, the negative or the change in the sign is affecting the x inside the absolute value. So if I were you, I would make note of this page, especially if you kind of have difficulty referencing this or seeing this, and just keep revisiting this as we go. So here it says combining translations. What is the graph of y equals the absolute value of x plus 2 plus 3? So to approach this, we can go ahead and break this down based on what we know from the previous slide and what we know from the previous section. So right off the bat, we already know that this is a translation up 3 from our parent function. But then if we go back to 2,6, we should reference or recognize that this is going to be a horizontal shift that is left 2 units. So what we can do is if we want to make just we'll just go ahead and plot the parent function, and then we'll just make our moves from there. So I'm going to plot just a couple of points. You don't have to use all of them. And so each one of these points has to be, in this case, shifted left and then up 3. Shifted left 2, up 3. So left 2, up 3. 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 Then I can go on this side, left 2, up 3. Left 2, up 3. And so this is what my graph of y equals the absolute value of x plus 2 plus 3 looks like. Here it's asking what is the graph of y equals x plus 2, or sorry, y equals the absolute value of x plus 2 plus 1. So same thing, let's deconstruct this. So we know that this is going to be a translation, up 1 unit, and this is going to be a translation left 2 units. Right, and so if we remember some values for our parent function, we've got 1. This is their parent function markings. We'll just do a couple here. And this time we're going to go ahead and shift it based on that information. So each one of these points is going to move left 2, up 1. And so this is our graph for y equals the absolute value of x plus 2 plus 1. Once you start to break down the transformations and how they apply to the functions themselves, graphing becomes a lot easier, especially when you know the parent function. So if you hadn't already noticed that the parent function of the absolute value function, so in this case y equals absolute value of x, has a slope of 1 on the right half of it, and the left half, or the left branch, has a slope of -1. All right, and so we're going to use that, and we're going to figure out how we're going to use this to help us apply vertical stretches and compressions. And so in this case, it says, what is the graph of y equals 1/2 the absolute value of x? So since we know the right branch of your original absolute value function had a slope of 1, now that they're trying to, in this case, compress it by 1/2, that branch's slope becomes 1/2 instead of 1. So if we wanted to draw just the right half of our absolute value, so we know that the absolute value parent function starts at 0, 0, and then normally has a slope of 1 over 1, so it would go here, 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 and here, but we don't want that. We want to apply the compression of 1/2, so instead of going up 1 over 1, we're going to go up 1 over 2, or up 1 over 2. I went up 2 over 1. We're going to go up 1 over 2, so we're compressing it, up 1 over 2, up 1 over 2, up 1 over 2. So now it's compressed on the right half here. But then remember, absolute value graphs are symmetrical, so what we did here, we could mirror to the other side, or we can remember that I said that the right half had a slope of -1, or had a slope of 1, and the left half had a slope of -1. So instead of thinking of it, all right, this was 1 times 1/2 gave us a slope of 1/2 now. Now we'll do the same thing here, take 1/2 times -1. This should have a slope of -1/2. But since we're going to the left, we're going to go backwards. We'll go up 1, left 2, up 1, left 2, up 1, left 2, up 1, left 2. This line, by working backwards, has a slope of -1, -1/2, sorry. And so this would be the graph of our function y equals 1/2 x, or 1/2 times the absolute value of x. Here we're going to apply the same rules. So it wants to know what is the graph of y equals 2 times the absolute value of x. Well, if we know that the slope of the right branch is normally 1, we would multiply that by 2, so the slope becomes 2. So we'll go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. So this is our right branch. We know that the left branch normally has a slope of -1, but now it becomes -2. But in order to apply the slope here, we'd have to go in reverse. So we'll go up 2, left 1, up 2, left 1. So we're essentially just making the mirror opposite to the right branch. And there we go. So this is y equals 2 times the absolute value of x. We can apply that same reasoning to get the graph of y equals -2/3, or -2/3 times the absolute value of x. So what we want to do is we want to start from here. 1 times -2/3 in this case is -2/3. So for this one, we're going to go down to right 3, down to right 3, down to right 3. Something's different here. We're not up in this quadrant with everything else. We're not up here anymore. We're now down here. Well, that's due to the fact that we multiplied by a negative here. That negative on the outside there has reflected our graph over the x-axis. Right. So let's go ahead and finish this graph. So we've got this half of our absolute value. Then we're going to do the same thing here. So this would be, on this side, we'd have -1 times -2/3. That becomes a +2/3. But since we're working backwards, instead of going up to right 3, we'll go down to left 3. Since we're going the opposite way we go normally when we apply slope. And this is the left branch of our absolute value function. And so there we have our two graphs. We've got y equals -2/3 the absolute value of x. And then here we've got y equals 2 absolute value of x. So this is called the general form of the absolute value function. In this case, y equals a times the absolute value of x minus h plus k. The stretch or compression factor is the absolute value of a, where the vertex is located at h and k, and the axis of symmetry is x equals h. So without graphing, what are the vertex and axis of symmetry for 3 times x, or 3 times the absolute value of x minus 2 plus 4? So if we break this apart based on what we just read, we should recognize that this is our compression value, or our compression or stretch value. we know that this value here is going to represent h. Well, actually, oops. This value is going to represent h, and this is going to represent k. Well, it asks for our vertex, so our vertex in this case is hk, so we're just going to say that our vertex is 2, 4. And then our axis of symmetry we read here is x equals h, and so in that case x equals 2. So our vertex and our axis of symmetry. The second thing they want to know is how was the parent function of the absolute value of x transformed? Well, in this case, so if we can kind of break this apart. Let's just write down here y equals the absolute value of x minus 2 plus 4. So we know that the plus 4 means it was shifted up 4. The minus 2 here, we went to the right, shifted to the right 2. And then this is going to be a stretch by a factor of 3. What are the vertex and axis of symmetry of y equals -2 times the absolute value of x minus 1 minus 3? How was the original parent function transformed? All right, let's just start by figuring out our vertex. Well, our vertex, remember, is h and k. So we've got h, and then we've got k out here is going to be -3 because it's supposed to be plus k. So we've got 1, -3. And then your axis of symmetry is just x equals h. So x equals 1. And then how was this transformed? Once again, let's just go ahead and quickly dissect it here. So we know that this is going to be shifted down 3. This will be 1 to the right. And this 2 is a stretch. And the negative part of it is also going to flip it over the x-axis. So we saw it flipped and stretched by -2, shifted 1 to the right, and then down 3 from its original parent function form. Here it wants to know what is the equation of each absolute value function. So we're going to go from the graph to the equation. So to start this problem, the first thing we need to do is identify the vertex. So for this one, for A, we have a vertex at -1, 4. We should also then notice that our graph is flipped over naturally. So we're seeing this flip, but we also see that the slope of our right branch went from being 1 to being down 1, right 3. So that's -1/3. So that's going to be our A value that affects how we apply this, because we're going to change our value on the outside. So remember, the general form for the absolute value is y equals A times the absolute value of x minus h plus k. We know that in this case, this is h, this is k, and we said that the right branch was changed from a slope of 1 to a slope of -1/3. So that's going to be our A value. So now we just need to plug this stuff in where it belongs. So y equals -1/3. We replace A, absolute value of x, minus a -1, so that'd be plus 1, absolute value, and then plus 4. Question B, same idea. Start by locating your vertex. Our vertex in this case, the vertex is at the point 2, -1. So there's our h and k values. Our right branch goes from having a slope of 1 to, in this case, it's going to be up 1, right 4. So that's a 1/4 value. So our A value is 1/4. And so now we can write our equation. We go back and we remember that the general form, y equals A, absolute value of x minus h plus k. And then we're just going to plug in those values. We've got h, we've got k, we've got a. So y equals 1/4 x minus 2 minus 1. And this is your equation for your absolute value function.